Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. It's my special pleasure to welcome Lakhdar Saiz today. He's a professor and delegate director at LENS, Center for Research into Informatics, that's CRIL, which is a collaboration between CNRS and the University of Artois. He's collaborated with our lab extensively in the past, and we're currently looking at new collaborations with him. That's why he's visiting us until Thursday. So if anybody has any questions or requests or just wants to know what we're doing, just come up to us or to him directly or to me to book some time. But before all of that, Lakhdar will tell us about connections between propositional satisfiability checking and data mining. Please.
Thank you, Christoph. You hear me? It's okay?
Yeah, it's on.
It's on. So, thank you, Christoph, for the introduction. And thank you for inviting me to be here. I have collaborated before with Microsoft Research with Youssef Hamadi since in 2007 until during 5 years. We have designed mini solvers, parallel solvers, SAT solvers, and so on. So I hope that we can restart the collaboration between CRIL and Microsoft Research. So. Thank you, everybody, for coming for attending my talk. The title is about cross-fertilization between propositional satisfiability and data mining. So it's the first work that connects these two domains. So this work is done jointly with Said Jabour from my lab and Yaqub Sarhi and Takai Keinu from Tokyo. And we have a web page dedicated to constraint and data mining, where we can find all our work in this web page. So we initiated this work during a French project which is called declarative approach for enumerating interesting patterns. The idea is to bring together pupils from several domains, such as database and artificial intelligence and algorithmics or combinatorics. So the consortium is made of CRIL from University of Artois and Limos from Blaise Pascal, Clermont-Ferrand, and Liris from Lyon. So this project is supported by the French INR Agency of Research. Okay. So what are the motivation behind this project is that, as we know, data mining are concerned by how to try to find something in the data, how knowledge discovery. This domain is mainly derived by real-world applications in many domains such as biology, business intelligence, web, etc. Okay. This domain is at the crossroad of many disciplines such as database, machine learning, statistics, and combinatorics, data, etc. So we have many applications in data mining. Pattern mining is one of the main themes of data mining. One know the original problem about basket data analysis proposed by Agrawal since 1994. There are plenty of such problems and even more applications on pattern mining and an overflow of research papers about that. Example, we know frequent Itemsets and variants, sequence, mining in trees, graphs, and so on. The motivation of our project is about that we know that we have a lot of contribution in pattern mining, different kind of patterns, various predicates of interest. Most of the work are focused on how to design efficient enumeration algorithm. Most are dedicated approach, but we one of the weak points is the lack of declarativity of this approach. So if we change slightly the problem statement, this requires a deep change in implementation, or implementing the algorithm from scratch. So the main goal of our project are, first, cross-fertilization between artificial intelligence, mainly constraint satisfaction problems and satisfiability, combinatorial algorithmics, and database. The goal is to bring original solution to fundamental pattern mining problem by designing high-level declarative language to describe data mining task. This research trend have been initiated by Luc Duret from Leuven in 2008. The principle used mainly content programming, for example, for itemset mining. The first paper in 2008. They encode both predicate and data as constraint satisfaction problem, and the solution to the CSP correspond to the pattern to enumerate. Okay? So this is a declarative approach, the first declarative approach. So if we change slightly the specification of the problem, we can add or change the constraint in the CSP. We do not need to implement the algorithm from scratch. So this is one of the main advantages of this kind of approach. In this talk, I speak about two things. I show how satisfiability can be used to encode data mining problems. And in the second part, I show how to use data mining for SAT itself, in both sides. In the first part, I speak about how to mine TOPCA frequent closed itemset mining using TOPCA SAT. So we define this problem and use it to encode this data mining task. Okay? In the second part, I show how to use data mining to compress propositional formula, to reduce the size of propositional formula. So I don't know if everyone is familiar with satisfiability, but satisfiability is a very well-known problem. First, I define what is called a conjunctive normal form, CNF and SAT, given a formula in conjunctive normal form, which is a conjunction of disjunctions of literals, where literals, a clause is a disjunction of literals X or not X, or its negation here. Example of formula, we have a CNF here, where we have the first clause, disjunction, P or not Q or not R, and the conjunction with other clause. Okay? So the SAT problem is to decide if such formula admits or not a solution. Okay? So this is the well-known NP-complete problem since Cook 71. So this formula, for example, have a model. So if we assign P to 1 and R to 1, we have partial interpretation which satisfies the formula. So the formula is satisfiable. If such an interpretation that satisfies the formula does not exist, we say that the formula is not satisfiable. So this is very simple, but hard to solve. Very simple to describe, but hard problem. Boolean satisfiability, we have seen recently since, I think, 15 years, since 2000. Spectacular progress. We now modern SAT solvers are able to solve instances with millions of variable and clause. So we started to look at applications. So many applications use SAT solvers. The traditional one is formal verification of hardware and software, planning, bioinformatics, cryptography also. So there is a competition each year on SAT, and these techniques, and there are also many works around SAT which extend the results from satisfiability to maximum satisfiability, weighted partial max SAT, QBF, quantified Boolean formula. These problems are either optimization or quantified problems. So we have two projects. The first one is I said some few words about that. With Youssef Hamadi, we have started working on SAT since during 5 years. And we designed one of the best portfolio parallel set solvers, for example, who dominated the competition during 4 or 5 years. And we have now a project with RATP France. We started this year about formal verification of software. We have solvers that can be found in our web page. So this is only the first. I limit the introduction about SAT to this. So what we remind that we have efficient SAT solvers that are used in application now, and we show the first use of SAT to data mining. Some notation before starting the encoding of the data mining text to SAT. I note L bar, the complementary literal of L, which L is a propositional literal, which is true or false. It's complementary. If L is equal P, then L bar is not P. If L is equal not P, then L bar is P. Okay, it's complement. For a set of literals, this notation means that we apply the complementary to each literal of the set. Okay, simply. L bar is defined as applying this as a set of complementary literals of those of L. By M bar, we denote the clause that we can obtain by negating all by complementing the junction of all the literals of M using their negation, the complement. Okay? If we have M is a model, for example, this is the clause that we get by negating each literal in the clause. Okay? This is defined like this. So we can, this can be used when we find a model, for example, when you enumerate for all models, this is the case for data mining, we add the negation of the model, the disjunction, to avoid searching for the same model after. Okay? And we note M of phi as the set of clauses satisfied by M, where a clause is a simple disjunction of literals in the CNF. And I use also this notation. It's simply, if we take a subset of variable x, of the variables of the formula phi, mx is simply the intersection m with x. It is the set of literals of x that are assigned true in M. Okay? And mx denotes the restriction of M to x. Okay? Because when we model some problems, we use additional variables. So we are interested on subset of variables. This is why I use this kind of notation. So after this preliminary, yeah.
I didn't understand the fourth line of my definitions. There's no phi on the right-hand side of the definition.
Where?
Fourth line, that one.
1, 2, 3, 4.
Yeah.
M phi
is phi a free variable, or
is the set of clauses satisfied by M.
What does phi stand for?
Die introduceert phi, de formula.
Phi is the formula, is a CNF formula. Phi is a CNF formula like this one. Oh, sorry. And this, I call this a clause.
Yeah, oh yes, okay.
Okay. Yeah. So M of phi is simply the number of clauses that are satisfied. We have a conjunction of disjunction. Okay. So M phi is the set of clauses satisfied by the interpretation. In phi, absolutely, yeah, yeah. And now I define, before encoding the top K item set mining, I define the top K models what in SAT, top K SAT. So I take a propositional formula, phi, and eta phi of phi is the set of models of phi. I note this, like the set of models, the set of solutions that satisfy the formula. Okay. I define a preference relation between models. like this. A preference relation over the models of phi is a reflexive and transitive binary relation, which is a preorder. Okay? Such that M is preferred than M prime. This notation means that M is at least as preferred as M prime. Okay? This is what I say, what is the preference relation over the models of formula is a reflexive and transitive binary relation. Okay? So this set, given a model M and the preference relation, this set describes the set of models that are preferred than M, that are better, given the preference relation. It's okay? We have a preference relation, which is a reflexive and transitive binary relation, and we define this set as the set of models that are better than N, according to this preference relation. Okay. Now, we can, as I mentioned before, when we model problems to SAT, we use extra variables. So I introduce here an equivalence relation modulo the subset of variables X. We say that M prime is in the same class than M2 prime if their intersection on X corresponds. The set of variables of X that are true in M prime is the same as the set of variables of X that are true in M seconds. Okay? So this equivalence relation introduces a partition of P with respect to this equivalence relation. So we restrict the relation to a subset of variables. Okay? So the Topka model, M is called the Topka model with respect to this preference relation and the subset X if the cardinality of the partition X is less than K minus 1. This is what I say Topka. It's okay. And this, we have a monotonicity property. If M is a Topka model and M prime is preferred than M, then M prime is also a Topka model. So we define this like that. Now, the Topka SAT problem we define is if we have phi or propositional formula and a preference relation over the model of phi, which is a preorder, and X a set of propositional variable and K a strictly positive integer, the goal is to compute the set L of Topka models with respect to this relation and X. This is the problem we define in SAT. So we have a preference relation between models restricted to the subset X, and we need to, the Topka SAT is to find the best K models of the formula phi according to this relation and to this subset X. Okay? Now, when we look for because this is an enumeration problem, we need to search for, all of these Topka models. So when we find one, we need to add additional clauses to avoid finding worse models, to get better models after finding one. So we define for that what we call eta preference relation, which is a polytime function from a Boolean interpretation. For example, if we find a model, we need to define a sort of lower bound. It is an application from Boolean interpretation to Siena formula such that for all model M of phi and for all M prime Boolean interpretation, M prime is a model of phi where we add this formula obtained from M, if only if M prime is the model of phi and M prime is better than M. So it's simply what I mean in this definition is simply when we have a model M, the eta preference relation is simply we have a polyterm function from M to CNF formula that we need to add to the formula to get better models, preferred ones. So if we add this, so we need to define for our problem in data mining this kind of lower bounds, and together with M bar, the negation of the model we found, this allows to find models M that are at least as preferred as M. So use lower bound, we need to define a lower bound, and we add the negation of the model found. So we restrict the search to only better models than those we have found before. So now, for example, I just mentioned that Topka-Sat is a generalization of, for example, of partial max sat. What is partial max sat is simply we have two parts in the formula, phi h and hard part and soft part. So the goal here, the goal here is to find an interpretation that satisfies the hard clauses, absolutely, and maximize the number of soft clauses that we need to satisfy. So this is the partial max sat problem. So phi h is the hard part and phi s is the soft part of the formula. So we define here is a preference relation on the soft part. This means that the model is preferred the M than M prime if and only if the number of satisfied clauses in the soft part by M is greater than the model, the number of clauses satisfied by M prime in phi s. Okay, this is the preference relation we define for this problem. The lower bound is simply this one. What we mean is that for a model, we generate this formula to get better solution after finding M. So we need to add a new additional variable for each clause, and we add this constraint to say that the sum of these variables may be greater than the number of clauses satisfied before by M. So we add the variable to each clause, and we add this cardinality constraint, this inequality, to say that we need to find better, to satisfy more clauses. Okay? So this is what I call the lower bound. So partial max sat can be defined in terms of Topka-Sat, as a Topka-Sat. Okay? No, the top one models of phi h with respect to this defined preference relation on the variables of phi correspond to the set of solution of the partial max sat. So Topka-Sat can be seen as a generalization of partial max sat. Now, after this definition, which are very hard, I try to show how we can encode data mining problems. I recall here the frequent itemset mining, the well-known itemset mining problem, given a transaction database. So here we have a set of items which are writers. Here we have the transactions, which are set of items here. So we define a support, for example, of Hemingway and Camus in this transaction as the number of transactions where this item set occur. Okay? This is the well-known item set mining problem. Okay? This is the notation of support. For example, Hemingway and Camus appears here and here. So the cardinality of the transaction where this subset appears is 2. This is the support of this item set. This is an item set. Okay? So frequent item set mining is the goal given lambda, which is an integer, positive integer, threshold. The goal is to mine or to enumerate all the item set that admit to support greater than lambda, which appears most than lambda in the transaction database. This is the frequent item set mining. Okay? For example, Hemingway, Camus, all these item sets occurs at least 2 times in the transaction database. Okay? This is the classical item set mining problem. Now, there are also, the output is exponential in general. So, many authors proposed condensed representation, such as maximal frequent item set or closed frequent item set. A maximal frequent item set is simply a frequent item set such that there is no item set containing it which is also frequent. It's the maximal one. So we can look for maximal frequent item set in the transaction database. For closed item set, it's simply frequent item set such that we cannot find greater an item set which include it with the same support. Support is the number of transactions where the item set appear in the transaction database. Okay? And it is closed when we cannot add another item while preserving the same, exactly the same support. If we add another one, it is not, we have different support. Okay? Now, our problem that we encode in SAT is defined like this. Given a transaction database, which is, as mentioned in the example before, from 0 to n minus 1, and we have T0 to n minus transactions, the output we need to enumerate is all frequent closed item set of length at least mean. This is defined in data mining problem, such that for each one there exists no more than k-1 closed item set of length at least mean which with support greater than its support. So we search for the top k and we impose that their length is at least mean. We have a transaction database and we look for all frequent closed item set of length at least mean. This problem, to encode this problem, we simply use, I will show the encoding, and then we use SAT solvers for enumerating the pattern. So we associate to each item a propositional variable, PA, and such Boolean variables are called the candidate item set. So when I have an item set I which is included in the set of items, PI, the propositional variable, is true if A belongs to such item set. Okay? And I associate also for each transaction a Boolean variable, BI. So we have a Boolean variable associated to each transaction. So as I mentioned in the example, I associate a Boolean variable for each transaction and a Boolean variable for each item. Okay? And now, how to encode the problem as a SAT formula? First, a constraint, we add this constraint, for example, here, to consider only the item set of length at least mean. If we look at the item set that have length at least mean, we add this cardinality constraint. The sum of PA must be greater than mean. PA is 0, 1 variable. PA is true if A is in the item set. Okay? As I mentioned, we have added each variable for each item, we have a variable PA. Okay? So those that are true, we have the sum. Those that are true represent the item set we found. So the sum must be greater than mean. So this constraint encodes the item set of length at least mean. This constraint captures all the transactions where the candidate item set does not appear. For example, here, I say that BI is associated to a given transaction, and we have a disjunction of PI here for all items that are not, if there is an item that is not in a transaction TI, this means that the item set do not belong to that transaction. So BI must be true. When BI is true, this means that the item set is not in the transaction. When it is false, the item set is in the transaction. So this formula encodes this. Capture all the transactions where the candidate item set does not appear. So we retain that BI is true when the item set do not belong to the transaction, and is false when it is in the transaction. Okay. A constraint to enforce candidate item set to be closed. The closedness constraint is simply saying that an item set is closed if there is no item set which contain it with the same set of support. This means that if I is closed, if we can add an item A and we have the same set of support, so we can need to add it. It is not closed. We need to add. Okay. This constraint captures the closedness. This means that if in each transaction where the item set appear, we have A which belongs to such transaction, so we need to force PA to be true. This encode this. If we have this support of I in the transaction, so the number of times it occurs in the transaction table is the same as the support of I union this additional item, then I must be in the item set. This is encoded by this Boolean formula. It's not, I don't know if you follow the encoding. So what I say, the first constraint simply encodes that the item set must be greater than, in size than mean. The second capture the transaction where the item set does not appear. And the third one encodes that the item set needs to be closed. Okay? So now, the proposition we have here is that computing the top K closed item set of length at least mean corresponds to computing the top K models as defined before of 1, 2, and 3. 1, 2, and 3. We have this encoding, and the top K models of the Boolean formula 1, 2, and 3 correspond to the closed item set of length at least mean. So what we have done is simply we modelized the item set mining, top K item set mining problem to SAT, and we look for the top K models. As I said before, with respect to the preference relation and the subset X, why I defined before some notation about X, because X, we have additional variable, for example, variables about transactions, but what we are interested only on the variables of the item set that encode the item set. PA, such that for all A is included in the set of items. And B here is the variable associated to transaction. We say that a model M is preferred than M prime if and only if it satisfies more clauses. We have more transaction where the item set occur. Okay. The pre-order relation is a eta preference relation because we can add a lower bound. Each time we have found a model, we impose that the next model must be better using this cardinality, linear inequality.
Can it be the same?
Huh?
Can it be the same?
It can be the same, yeah. So to obtain closed item set with support greater or equal to the support of the closed item set obtained from M, this is the lower bound. what I defined previously is that given a model, it's an polytime we have a polytime function that from the model we generate a formula, which is a constraint. Okay? We need to add to the formula to enumerate better models. This is declarative because if we want now to look for mining Topka closed Itemset of length at most max, we need simply to add this constraint. The sum must be greater, less than or equal to max, this linear inequality. Okay? And if we want to mine closed Itemset of support at least lambda, we need to add this. I just require that BI is true if the Itemset do not belong to the transaction. So BI bar simply means that the transaction, if this means that this encodes that the number of transactions where the Itemset appear must be greater than lambda. So it's a simple constraint that we need to add. So the model can be, if we need to add, to modify the specification of a problem, we need to add constraint to the model. As you have seen, many of these constraints are linear inequalities. So how to translate this to CNF, to Boolean formula? This is what we call the cardinality constraint, or 0-1 linear inequality. The sum from E equal 1 to n of xi, which is 0-1 variable, must be greater than lambda. In most of the constraints, we have this linear inequality. So there are many works that try to encode this, because in SAT we do not know how to count. So many works, each year there is a new encoding about how to encode linear inequalities to SAT. And we started looking at this encoding, and on the first paper that proposed the encoding of linear inequalities to SAT, we have found that there is wrong for formulation in one page, and after correcting that, we found a new encoding that we called a pigeonhole-based encoding. I don't know if you know a pigeonhole problem, which is how to put n pigeon in, or lambda pigeon in n holes, and in n-1 hole. The problem is inconsistent in general. This is what the well-known pigeonhole problem. So to encode this linear inequality, to say that the sum of xi from 1 to n must be greater than lambda, can be encoded using the pigeonhole formulation. This means that how to put lambda pigeon in n holes. If we formulate this problem in CNF, so we have the encoding of the linear inequality. This is, I explain quickly this encoding. This disjunction, for example, we have lambda pigeon and n holes. Okay? PKE express that the pigeon K is in hole E. This means that the pigeon K, this disjunction, the pigeon K is in hole 1 or in hole 2 or in hole lambda. Okay? So this formula encodes that we do not leave the pigeon free. Okay? Each pigeon must be put in one hole. And this second formula mentions that if we have two pigeons K and K primes, they cannot be in the same hole. Not PKA or not PK prime I. Okay? This is the pigeonhole formulation. And we have a connection between the variables of the pigeonhole problem and the xi of the formula. Xi is true if the hole E contains one of the pigeon K from K to lambda. Okay? So this is a simple formulation using the well-known pigeonhole problem. And it is the number of additional variables that we add here, because we have added the p variables, is lambda square times n, and the number of clauses is n times lambda square. However, if we use, I don't know if you have understand this encoding. It's difficult. How to put lambda pigeon in n holes. This clauses encode that the pigeon k must be in the hole 1 or the hole 2 or the hole n, okay? From e equal 1 to n. This is disjunction, okay? And this binary clauses, because containing two literals, means that the pigeon k and k' cannot be in the same hole I, okay? And if we have the pigeon k in hole I, so xi must be true. They have a connection between the formulation of the pigeonhole and the xi of the formula. So the models of this CNF formula correspond to, restricted to x, to the variables x, correspond to the solution to this, of this linear inequality. I skip the next because, as you know, pigeonhole is difficult to solve. To get a better encoding, we use symmetries to reduce and to make the encoding more efficient. We have symmetries between the pigeons and holes. So we use symmetries to obtain a better encoding, because if I visualize, for example, this constraint, which is disjunction, as a matrix here, we can permute two rows, any two rows, and we leave the formula unchanged. This is a symmetry of the formula before. Okay? So the set of symmetry is given here. If we swap two rows from this is a disjunction that I said before. The pigeon 1 is in hole 1 or in hole n. Okay? The pigeon 2 similarly. And using this symmetry, we get a better encoding. I skip how we can break symmetries because I need another talk about that. But we obtain this complexity, an encoding using the pigeonhole principle of this linear inequality, which can be decided by unit propagation efficiently. There are other encodings that are better. For example, the best one is the cardinality networks, which is n logarithm of lambda. So in this first part, I explained that we can simply encode data mining, many talks of data itemset mining, for example, in SAT. The second part is less complicated than the first, is how to use data mining to compress Boolean formula. The motivation behind this second part of our work come from that as SAT technology is now, we have a growing success obtained by solving real-world problems, an increasing use of SAT technology to solve a real-world application, but we observe a rapid growth in the size of the CNF instance encoding real-world problems. We have very, very huge instance now. So the challenge is to design a new efficient models for representing and solving SAT instance of very large size. Okay? So what I will show, for example, when we encode problem in SAT, for example, like Sudoku, we associate to each cell n propositional variable, and simply by adding the clauses that need to encode that each cell contains at least one value, we have n square clauses of size n. And we get a huge formula, usually. So in many real-world applications, we have, for example, this is a CNF formula in SAT, in Dmax format, where numbers correspond to literals. For example, this is x1, this is x2, not x3, and so on. So each line is a clause, a disjunction of literals. So we have CNF that have 11 million of variables and 32 millions of clauses. And this instance encode a bounded model checking problem. So that we have huge instance, but as we can see, these clauses, we have disjunction here, so each line is a clause, correspond to some structures. So what I want to do is to use data mining to extract patterns and to use such patterns to reduce the size of the formula. And for that, I use extension principle. For example, when we find the patterns, we introduce new variables and we substitute such pattern by the new added variables. You use extension principle proposed by Tseitsin in 1965. For example, if we have a DNF here, which is disjunctive normal form, and or, okay? If we want to translate this to CNF without adding variables, this is exponential. We need to distribute the and with the or, okay? And we get this formula. But if we add new variables, for example, we add new variables to say that Z1 is equivalent to this, Z2 is equivalent to this formula, we get this disjunction and this one. So the translation using additional variable is linear. Okay? So Tseitsin encoding is used to translate arbitrary Boolean formula to CNF linearly, but we get a new formula which is equivalent only with respect to satisfiability. Okay? So we use the Tseitsin principle to compress the formula. And extend, I think I speak, because extended resolution proposed by Sin, adding new variables can also be used to improve proof systems, the efficiency of proof systems. So how we can do how we can use data mining to compress? We can see a Boolean formula as a transaction database. Simply, this clause can be seen as an item set, okay, as a transaction. Each clause is a transaction. So the goal is to reduce the size of the formula, reduce the number of literals using the frequent sets of literals and Tseitsin extension principle. So we search for frequent item sets in the transaction database that represent the Boolean formula, the CNF formula, and we introduce new variables to reduce the size. So, for example here, we have a CNF formula where x1 to xn occurs in these clauses from 1 to k. So what we do is to add a new variable y, and we replace this item set, this subset that occur in all these clauses, and we need to say that y is equivalent to x1 to xn, but it is necessary, the implication y is imply x1 xn is sufficient in the transformation. We can add the equivalence between y and x1 to xn. So we replace this one and we say that y, the new variable, is equivalent to this, but the restriction to an implication is sufficient. So we substitute n times k literal, because we have n literals, which appears k times. We substitute them with k plus n plus 1. Here, each one is replaced by y, is corresponded to k, and we add this new clause, which corresponds to n plus 1 literal. So we substitute n times k by these literals. Okay. So the size reduction can be the difference between the number of literals substituted by the other ones, n times k minus this quantity. So the size reduction must be greater than 0. So we can find the k in function of n, which is the frequency that we use, or the threshold that we use in the item set to find such patterns. And we use closed item set instead of maximal because it is better to use closed item set to reduce. I skip this slide. And we have also, but just to mention, we have some problems that if we have X and Y, which are item sets that overlap, their intersection is not empty. So we define here an equivalence class with using this relation. And we say that an item set Y is in the same class than X if we have intersection between Y and X, and we have Y with Y1 and Y2 and so on. So we can find a path from Y to X by intersection. Okay. And the optimal solution when we substitute, well, because we find many patterns, so which one to use to compress. So the optimal solution we search for can be restricted to the optimal solution in an overlap class. So if we have item sets that do not share anything, we can find optimal solution for one class than for the other. So we have not used an optimal solution, but we have used a greedy algorithm. I have 5 minutes. The greedy algorithm is simply like this. We have a formula phi and an overlap class of closed frequent item set that we search on the transaction database that represents the Boolean formula. And we rank all the patterns that we have found according to their reduction. I did not explain this before this one. We associate the weight to frequent item set, for example, X that appear in the formula. This is the support, the number of times where X appear. This is the size of X. So the size of X times the number of times we support. This is the reduction we get. Minus we add a new variable each time X appear in the transaction database or in the formula. So we add Sx times the new variable, and the new clause that we add is of this size. So the difference measure the weight the reduction of such item set on the CNF. So we order all the item set we found using the data mining technique according to this measure, and we use a greedy algorithm. So the greedy algorithm is described. We get the most interesting one according to this measure, and we replace it, and we add the new formula, we substitute, and etc. What I will show to you is that on industrial SAT instance, there are here. So I give here some instance, SAT instance. We have the size of the formula, original size, the compressed formula, and the percentage of reduction. For example, on some formula we have good rate of reduction using this technique. For example, on this many times. So we get several reduction. As I have only 5 minutes, another thing that I have not said, I want to say something, is about binary clause. In industrial instance, many CNF contain clauses of size 2. So this, if we map this to transaction database, we have transaction with only 2 items. We have, in the first experiment, we have not used these clauses in our reduction. So many instances contain these binary clauses and a percentage which is very high. So how to reduce the binary clauses? For example, like this, that we have clauses of size 2. And how to represent this. As I have no time, I just show you how we write such formula as follow. For example, here we have x1 or x2, x1 or x3. We can write this as x1 or a conjunction of this using an ordering on the variables of the binary. So we get what we call B implication, which is x1 or a conjunction of literals, x2 or conjunction of literals, and we do our mining on the conjunctive part. So when we find items here, item set with frequent item set, for example, x5, x6, x7 now occurs 4 times, we replace such item set and we can reduce binary formula. It's complicated, but in the conjunctive part. So we rewrite the binary clause as a disjunction with a conjunction using an ordering on the variables, and we mine on the conjunctive parts and we substitute in similar way. So what I say is that, for example, if we have cliques or big cliques of binary clauses, applying our technique, we can get this kind. We have n. This figure means that we have binary clauses between x1, xn, and y1 and ym. Okay. So we reduce from n times m binary clause to n plus m binary clause for big clique, and from n squared to n for cliques. And we get further reduction using binary clauses. And in this case, we have also gain in solving time on compressed or on the original formula. And our technique can be used for graphs. We are generalizing because we are actually looking for how to use this technique to compress graphs. And we formulated this as an optimization problem also. Okay, I have not time to explain. So, as a perspective, we are working on how to enhance our encoding and using partition-based set encoding for item-set mining, because I have not said that on the efficiency we are not, dedicated approach are more efficient than ours. But recently we have proposed a partition-based encoding, and the gap is significantly reduced between the dedicated approach and our declarative one. So we are thinking about compressing graphs and hypergraphs, and how to discover structure in Boolean formula, other structures than item set, for example, dependency, Boolean functions, and so on, using data mining techniques. So thank you for your attention. And if you want to look at this, you have a web page and some publication that on this research issue. Thank you very much.
Maybe a quick question or two. Anybody have anything quick?
Quick one would be how long does the compression take? And when you present the comparison in runtime between the compressed and the non-compressed runtime, is that including the time it took to actually?
Yeah, including the time, yeah.
Thanks, Dr. again.
Thank you very much.